I welcome you to this class of econometric methods. Myself, Dr. Muhammad Imdadul Haq, an associate professor at the Department of Economics, Aligarh Muslim University. See, the majority of work in econometrics, it focuses on structural estimation, which involves estimating the parameter or the relationship defined by mathematical economic theory. So, and up to this point, we have solely addressed the estimation methods and challenges of individual relationships among economic variables. However, economic model often entails a network of relationship. Clearly, in these instances, relying on a single equation model cannot be justified. So, in today's lecture, we move to the realm of simultaneous equation models. It is a system describing the dependence of variables, the joint dependence of variables, and this is what we refer to as simultaneous equation model. In real-world scenarios, economic variables frequently demonstrate complex interdependencies with concurrent interactions amongst them. Consequently, there are instances where isolating a single equation for independent estimation proves a bit of impractical. Parameter estimation of the equation must be carried out simultaneously within the comprehensive model. The number of equations in such model, it will depend jointly on the how many endogenous variables are there, and things we will see in the coming discussions. So, to have a feel of what do we mean by joint dependence, excuse, what do we mean by joint dependence? See, CT is a function of YT. Good. This is very plausible that consumption is a function of income. But if you just recall your chapters of national income determination, YT is also determined by CT. We are ignoring G, or if the normal Keynesian equation Y is equal to C plus I plus G. So at the moment we ignore G. So what I want to emphasize is YT was till now we were using in the terminology we will be using independent and dependent variable. So YT was the independent variable, but the same independent variable is also a dependent variable, and the dependent variable, it becomes an independent variable. As such, I should not be using this word dependent variable and independent variable, because in the discussions on simultaneous equation model, there is no as such a dependent variable as an independent variable. The same variable which is dependent at one time, it becomes independent at the other equation. Rather, we refer here as endogenous and exogenous. So we will see it. Now, so there is an element of joint dependence. Or with the help of another example, we can see that there is a two-way causation. Two-way causation means, so let's take a demand equation. That is B0 plus B1P plus B2Y. Okay, Y is not a point of our discussion at the moment. It is, depends upon price. Price is the independent variable. Okay, agreed. But it's in reality, quantity demanded is not only a function of price, but price is also a function of demand. And that is the reason what we are doing, we are introducing the supply function also. So quantity supplied is a function of B0 plus B1P, that is price, and B1W we can take it as weather, and U. So P is present over here also, P is present over here also. And as a matter of fact, demand and supply determine the equilibrium price, and price in turn determines the equilibrium quantity demanded and quantity supplied. So if we are studying a single equation model, this is not exactly defining the situation which is in reality. And the third equation is quantity demand is equal to quantity supplied. Based on this and the demand function and the consumption function, when we estimate a model, this is comes under the domain of simultaneous equation models. Some of the terminologies which we will be using commonly over here are endogenous. The first one is endogenous and exogenous variables, and then we have structural model, reduced model, and final form model. Let's see what's an endogenous and exogenous variable. It is a corollary of your independent and dependent variable. What was dependent over there is endogenous over here, and what is an exogenous in a normal, what is exogenous over here in simultaneous equation model is in a single equation model is the independent variable. So C and I. So, but we have a way to look at it. CT and YT, they are being determined after solving this system of equations. So, that is why we call them endogenous. And something like IT is being given from outside, is something which is, we are not deciding what will be IT in the model. So, something which is not being decided in the model is referred to as exogenous. So, if you want to define, endogenous are those variables whose value is determined within the model, and exogenous are those variables whose value is determined outside the model. Or we can say that the unknowns are endogenous and the values of exogenous are given in the model. So, I hope this is what, instead of referring to independent and dependent variable in our upcoming classes on simultaneous equation models, we will be referring to as endogenous and exogenous variables. Now, a model like a model which we have, say Ct is equal to alpha plus beta yt plus ut, and yt is equal to Ct plus it. This model was simply referred to this system of models as a structural model. It means it is describe the structure of economic relationship with the help of an equation. Here endogenous variables may be expressed as a function of exogenous or predetermined variables, some whose values we are knowing. Now in predetermined values, it can be a lagged endogenous, like if we have an element of beta yt minus 1 y1, it was beta plus beta 2 yt minus 3. But consumption of today depends upon the income of the previous time periods. And exogenous variables are also called as endogenous variable. So this particular system of equation is simply referred to as the structural model. Now, from those same structural models, we can derive the reduced form models. The reduced form models. So here the endogenous variables are expressed as a function of exogenous, or you can say predetermined variables only. How we have got it, we will show to you at just after a few moments. But at the moment, what we understand, Ct, okay, is an endogenous variable, yt is an endogenous variable, and it is being explained as a function of it. It is an exogenous variable, it is a predetermined variable. Again, yt is also being explained as a predetermined variable. So here we do not have any variable which is in one of the equations as, say, an exogenous variable, and in the other equation it becomes an endogenous variable. So that situation is not present. Like we have that model Ct is equal to alpha plus beta yt plus ut, and we have yt is equal to Ct plus it. This is not a reduced form model. No. The reason, this yt is an exogenous or predetermined as such over here, and this yt is again endogenous over here. So here it is exogenous and here it is endogenous. So this is this example is not an end and case of reduced form model, but this is a reduced form model. And how we have got it, we will see it. Just Let us do the preliminaries first. Then we have final form model. Here endogenous variables are expressed as function of only exogenous variables, and that's all. Now let us see the difference. See, conceptually, the distinction between a structural and reduced form model is that the coefficient of a structural model show only direct effect. We will understand what is a direct effect just a second. Whereas the reduced form model, they show the direct and the indirect effect, that is the total effect. And the difference, it's not here mentioned, the difference between this lagged endogenous, if the difference between reduced form and final form model is only the presence of lagged endogenous models. If the model does not have any lagged endogenous variable, then the reduced form model and the final form model, they are the same. But there is a difference between structural and reduced form. In structural, this is endogenous variable yt is present as a function of, endogenous variable is a function of an endogenous variable itself. This yt is also endogenous in the same system of equations. And in the second equation, endogenous variable is a function of predetermined, that is it is also a predetermined. So here we are getting the direct effects. When we move on to reduced form models, here there is no element of either y, or here there is no element of c. Since there are no elements of that, so Ct is being explained as a function of it only, and yt is explained as a function of it only. So if this being the case, then this is a reduced form model. Now, our good old friend, that is our ordinary least squares method, that can, if we apply this our ordinary least squares method over here in simultaneous equation modeling, we will fall into issues, and those issues are the estimates are biased and inconsistent, and u satisfies all the assumption, but still there is a problem of joint dependence of the variable. We will see in detail. We take a system of structural equations. This is our structural equation model. Here estimator of beta is biased as well as inconsistent. We cannot apply OLS because the correlation between yt and ut. But beta can be estimated directly. There are many methods, we will see that also. Now, so what we do, first obtain the residual form of the model, that is then we will do in the reduced form, the reduced form of the model. And in the reduced form, there is no correlation between Ct and it, and it and yt is a function of it only. There will be, if we in the reduced form, there is no problem, then we can do OLS and estimate. So the reduced form models, those don't have a problem, but if we simply apply OLS to the system of equations which are in the form of a structural model, then we are our estimations will have issues, and we will see what are the estimation issues. Now first let us derive the reduced form models. We have our function, we have our same old equation, Ct is equal to alpha plus beta yt plus ut, and yt is equal to Ct plus it. This is what we have. Now, in place of y, we are writing this. We are incorporating, in place of I, we are incorporating Ct plus it. So this is just yt, in place of yt, we are writing Ct plus it. Now, then we open the bracket, beta Ct is plus beta it, alpha plus beta Ct plus beta it is ut. Now, this, since there is a Ct element over here, we take it to the left hand side. So, Ct minus beta Ct is equal to alpha plus beta it plus ut. Now, what we can do, we can take Ct common. So, see, when taking Ct common, we have 1 minus beta is equal to alpha plus beta it plus ut. This we can write it in terms of Ct only, and this is my reduced form model. We got it from the from this, these two structural equations can be reduced and Ct can be written in this format. That is Ct, I am taking 1 minus beta to the right hand side, this is to the right hand side, and the denominator it will be coming. So Ct is equal to alpha 1 minus beta plus beta it divided by 1 minus beta plus ut divided by 1 minus beta. Now the same thing we will be doing for yt. You have what is your equation in Ct was equal to alpha plus beta yt plus ut, and we have here yt is equal to Ct plus it. In place of Ct we incorporate this entire term. So now we can write this is Ct, that is alpha plus beta yt plus ut, and then it comes as it is. We take the yt terms, this term to the left hand side, so it becomes yt minus beta yt is equal to alpha plus ut plus it. Now taking 1 minus beta yt common, we have yt 1 minus beta is equal to alpha plus it plus ut. Now we can take 1 minus beta to the right hand side, it will come in the denominator. So yt can be written as yt is equal to alpha divided by 1 minus beta plus 1 divided by 1 minus beta it plus 1 divided by 1 minus beta ut. So using the system of equation, this is what you had, this structural model. We can write this yt in the reduced format. Now we again take both of these two equations, we incorporate. I think this is a repetition, just for a moment ignore this slide. This is just a repetition of this current slide. So we ignore it for a moment. Now we start it from here. Yt is equal to Ct plus it. Yt and Ct we know is equal to alpha plus beta yt plus ut plus it. We take the betas over there, so we get this in the form, we can write it in the reduced form. Now we take the expectations. The moment we take the expectation of yt, this equation we want to take the expectations of. So expected yt is equal to alpha 1 minus beta, it's a constant term, plus 1 upon 1 minus beta it, okay, and expected value of ut by assumption is equal to 0. So this entire term gets cancelled. Then what we do? Then we have our equation of yt, and this is an equation of expected value of yt. So yt equation is alpha 1 minus beta plus it 1 minus beta plus ut divided by 1 minus beta minus expected value of yt. This is equal to minus alpha 1 minus beta minus it divided by 1 minus beta. Now it 1 minus beta, it 1 minus beta cancels out. Alpha 1 minus beta plus, and here it is minus alpha 1 minus beta, they cancel out. So you are left with yt minus the expected value of yt is equal to 1 upon 1 minus beta multiplied by ut.